PowerPoint and talk to you about mass numbers and isotopes. Now, from junior cert, you remember that the mass number is the bigger number when you look at the nuclear formula on the periodic table. So the bigger number here for carbon is 12. So what does that tell me about an atom of carbon? It tells me the number of protons plus the number of neutrons. Now I know, so it's the mass of an atom. It's what's contributing to the mass of an atom. Remember, electrons mass are negligible, so we don't include those. Here is the atomic number, it's the smaller of the two numbers. And remember that atomic number tells me the number of protons. So by subtraction, I can find the number of neutrons in an atom. So that's mass number, bigger number, and tells me the number of protons and neutrons, how heavy an atom is, the mass of an atom. Isotopes then are atoms of the same element. So for instance, with carbon, you can get 3 different varieties of carbon. They all have an atomic number of 6, okay? But you can get carbon 12, carbon 14 atoms, and you can get carbon 13 atoms. So you have 3 different forms of carbon. They're all atoms of carbon because they all have an atomic number of 6. If they were atoms of nitrogen, they would have an atomic number of 7. So atomic number is unique to an element. If the atomic number changes, the element is different, okay? So atomic number is unique, but mass number, you can have different forms of carbon. Some of the carbon atoms are heavier than others. So if you subtract here, this one has 6 neutrons. This carbon atom has, 7 neutrons. And this one, 6 from 14, has 8 neutrons. So you have different forms of the same element. Okay, so different atoms of the same element because they have different mass numbers. And why is that? Because they have different numbers of neutrons in their nucleus. Okay, now hydrogen is another example. So you can get hydrogen as hydrogen 1, hydrogen 2 and hydrogen 3. The atomic number of hydrogen is 1 all of the time. So they're isotopes of hydrogen. This has no neutron. Okay, this form of hydrogen has 1 neutron and this form of hydrogen has two neutrons. Now, how would you know what the mass of one hydrogen atom would be? How would you know what the mass of one carbon atom is going to be? You have to get an average value taking the abundance of the isotopes into account. So if I said to you, I've got a sample of carbon, 90% of it is carbon 12, 5% of it is carbon 13, and the other 5% is carbon 14. How would you know what the mass of one carbon atom would be? Okay, how would you figure that out? Well, what you'd have to do is you'd have to say to yourself, well, 90 out of 100 atoms have a mass of 12, 5 out of 100 of the carbon atoms have a mass of 13, and another 5 out of 100 have a mass of 14. And then you multiply 90 times 12 comes out to give you that 65 and 70 when you multiply. So your total when you add it all up there is 1,215. But that's for 100 carbon atoms. So how would you calculate the mass of 1? You divide by 100. So the mass of 1 would be 12.15 atomic mass units. Okay, 12.15 atomic mass units. So if you go to the periodic table then, if you look across on the periodic table, you will notice that mass numbers have decimals. So like we got 12.15 there as the average mass of an atom of carbon because we had to take into account the abundance of the different varieties of carbon or the abundance of the different forms of carbon that you can get. Okay, now on page 24 of your revision book, he does out an example 4.1 where he uses a sample of boron. He says that you've got 18.7% boron 10, 5 is the atomic number, and you've got 81.3% boron 11. Again, it has to have the same atomic number. How would you now calculate the average mass of one atom of boron? Well, same way, you would say, well, 18.7 out of 100 atoms of boron have a mass of 10. 81.3 out of 100 have a mass of 11. So then you would multiply that and you're going to get your 187. When you multiply that, you get 990.3. And then when you add that up there, you're getting 1081.3. But that's for 100 atoms. So then you have to divide by 100 and you'll get your 10.81. And if you look up at the periodic table, you'll see that the mass of one atom of boron is not a whole number. There's a decimal point because it's an average value. It's not because you can have 0.8 of a neutron. Okay, because if you look there for a second, like boron's atomic number is 5, and we're after saying there 10.81. When you subtract that, you're getting 5.81. It is not possible to have 0.81 of a neutron. The decimal place comes from the fact that these atomic masses are average numbers, taking the other isotopes into account. Now, I just want to get Dropbox there for a second, and I just want to just to run through those few slides that I'm after kind of dealing with there. Now, we've stopped here on where the electrons are. So Bohr's theory was that electrons travel in orbits or shells around the nucleus. Okay, and we'll talk about Bohr. We'll talk about Bohr again. Now, you know from junior cert that protons are positively charged. They're found in the nucleus, and you know about Rutherford's discovery of the nucleus and Rutherford's discovery of a proton. And you would know this table from junior cert. So the charge of a proton is plus, its mass is 1 AMU. Electrons are -1, they don't have any mass really, they have negligible mass. And the neutron has 0 charge but a mass of 1 AMU. Okay, so this is it. Now, atomic number is the number of protons, okay, and there's the same table again. Atomic number is the number of protons, and 47 there is the smaller number. That tells you the number of protons. Number of protons has to equal the number of electrons, and then the mass number of the number of protons and neutrons. What are isotopes? They're atoms of the same element. So they're atoms, same atomic number, same number of protons, but different number of neutrons. And there you have your hydrogen examples, H1, H2, and H3. Okay, carbon is also found as C12, C13, and C14. Okay, now here, look, in the periodic table, mass numbers are not whole numbers because the numbers of neutrons present in the nucleus of one atom of a particular element is different from that of another atom of the same element. They're average values, and that's where the decimal places come into play. Okay, and that's a definition then of relative atomic mass. So what's relative atomic mass? It's the mass of one atom of an element, and the mass of an atom is measured in grams. It's very, very small. Therefore, it's more convenient to express the mass relative to 1/12 the mass of the carbon-12 isotope. So we express the mass of all atoms. We compare it, or we express the mass of it relevant to 1/12 the mass of carbon-12. Why a 12th of carbon-12? Because that's what 1 AMU is. Okay, so that's your definition now, look, of relative atomic mass. The relative atomic mass of an element is the average mass of an atom of the element relative to 1/12 the mass of the carbon-12 isotope. And this is showing you like an example of the calculation that I did on the board there a while ago. Okay, now one last thing that I wanted to do is this would be information that you would get from a mass spectrum, which is an instrument that we're going to deal with tomorrow. Now, a mass spectrum for something like mercury. Now, if you can see there, just a second now, and I'll just show you the values. Mercury, what information does this mass spectrum give us about mercury? So firstly, it tells us how many isotopes of mercury there are, because you've got a peak here, you've a peak here, 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 and here. So it gives you, this is the information I suppose this mass spectrum is going to tell you. So it tells you that there are 1, 2, 3, 4, 5, 6, 7 different isotopes of mercury. They're all atoms of mercury, but they have different numbers of neutrons in their nucleus, so their masses are different. So you have mercury 196, mercury 198, mercury 199, 200, 201, 202, and 204. Now, what other bit of information does the mass spectrum gives you? Well, it gives you the relative abundance of each of these different forms of mercury atoms. So it tells you that there is, look, 0.146% of the atoms of mercury have a mass of 196. It tells you that 10.02% have a mass of 193, and so on. So what can you now do with this information? So you can now calculate the average mass, the relative atomic mass of one atom of mercury. So I want you to do that now, and I want you to email me the answer. Okay, thank you.